Okay, let's talk a little bit more about Taylor's theorem. So let's recall from chapter 5 that Taylor's theorem says if we have a function f is k times differentiable, say k plus 1 times differentiable, then at a, then f of x is equal to the sum from n equals 0 to k of the nth derivative at a over n factorial times x minus a to the n plus, so this is the Taylor polynomial, plus some error term, and that error term is at the k plus first derivative some value x star times x minus a to the k plus 1 over k plus 1 factorial. And this x star is between x and a. Okay. So if it's just k plus 1 times differentiable, I can get this polynomial approximation, and I can bound how big that polynomial approximation can, or an error can be. So if it's infinitely differentiable, we can sort of now use our series and prove when that series actually converges. If f is infinitely differentiable, f of x is equal to the sum from n equals 0 to infinity of f sub f of n, the nth derivative, at say at a over n factorial times x minus a to the n. And now we get to say for all x in the radius of convergence, which is defined by say alpha equals this lim sup of the nth root of f of n a over n factorial in the radius of convergence 1 over alpha, where alpha is equal to this lim sup. So for x in a minus 1 over alpha to a plus 1 over alpha. And we would have to test the endpoints to see if it works out there, but we at least know that it's true in there. And in fact, we've got uniform convergence of these polynomials inside that interval, Okay, so we're going to use this, and we're going to come up with some nice ways to write functions. So like the sine function, the cosine function, the exponential function, the logarithmic function, and so on. Okay, so some common Taylor expansions. Taylor series expansions. We've got e to the x, and it's equal to the sum from n equals 0 to infinity of x to the n over n factorial. we've got the sine of x is equal to the sum from n equals 0 to infinity of negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial. Cosine of x, sum from n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. And let's go with the natural log of 1 plus x is equal to the sum from n equals 0 to infinity. I think I've got negative 1 to the n, x to the n over n. Let's check this one. That one I'm not quite sure on my memory. So let's see how we actually find these given a function. So let's look at the natural log of 1 plus x and see if we can show that it's equal to this sum that I think I have in my memory. So what are we going to do? Well, each of those terms in the Taylor series looks like an nth derivative at some value. Well, I want to center this at 0, so I want the nth derivative of 0 of this natural log of 1 plus x function over n factorial times x to the n equals 0 to infinity. So we need to compute the nth derivative at 0 for f of x equal to the natural log of 1 plus x. So let's try and do that. F of 0, the 0th derivative, is equal to the natural log of 1, which is equal to 0. So that's probably good here. Let's look at this. I probably don't want to start at 0 because I'm dividing by 0 there. So we probably want to change that. We probably want to start this at 1. Let's see if we're good for the rest of it. F prime at 0. Well, if I take the f prime at x is going to be 1 over 1 plus x. So that's going to be 1 over 1. That's going to be a positive 1. If I look at this, I've got at 1, I've got a negative 1, so maybe I think I'm probably going to want a plus 1 there to make that positive. I think we're going to be good now. So let's see how we find the rest of these. The second derivative at x is going to be, well, I can sort of use a chain rule type thing. This is 1 plus x to the negative first. Sorry, this is 1 plus x to the negative first. So what I'm going to get is I'm going to get negative 1 times 1 plus x to the negative second. So f double prime, or the second derivative at 0, is going to be negative 1 times 1 to the negative second, which is negative 1. We might just have to scratch that and figure out what this is going to be. So I've started out 1, and then I go negative 1. Let's look at the third derivative at 0. Well, I get to do the chain rule again. So this is going to be negative 1 times negative 2 times 1 plus x to the negative third is positive 2 x to the plus 1 to the negative third. So this is equal to 2 at 0. The fourth derivative at 0 is going to be the fourth derivative here at x. Well, what comes down is I've got negative 3 times 2 x plus 1 to the negative fourth. So what it looks like is each time I'm going to be increasing the factor by the derivative that I'm taking, right? So minus 1. So this is going to be negative 6. The fifth would be positive 24. And it looks like the nth derivative at 0 is going to be negative 1 to the n plus 1 times n minus 1 factorial. Okay, so this implies that C sub n, let's check if that works for 0. Negative 1 to the 0 plus 1 is negative 1, and negative 1 factorial is 0. So that doesn't quite work for the 0th term, but it should work for the first term because 0 factorial is 1. Yeah, so it works for the first term. It doesn't work for the 0th term, but the 0th term is 0, so I can kind of just omit the 0th term. So what we get is negative 1 to the n plus 1 times n minus 1 factorial over n factorial, and this is for n bigger than or equal to 1. Okay, so natural log of 1 plus x should equal, well, n minus 1 factorial on top is going to get rid of that factorial there. I'm going to have the sum from n equals 1 to infinity. The 0th term, remember, was 0 because right there f of 0 is 0. So I get negative 1 to the n plus 1 over n times x to the n. That might have been what we had up there after we modified things a little bit, but this is sort of how you compute a Taylor series. There's the Taylor series for a natural log of 1 plus x. Why did I do the natural log of 1 plus x and not the natural log of x and trying to center it at 0? Well, if I try to center the natural log of x at 0, what is the natural log of 0? It's undefined, right? So I have to pick some other point to center this natural log function at, or I have to shift it at some other value. So I could center the natural log of x at 1, and how do I go from here to here? Well, this natural log of x is equal to the natural log of 1 plus x minus 1, right? And so if I wanted to put this into this Taylor series, I could write it as the sum from n equals 1 to infinity. And now what am I plugging in here? I'm plugging in x minus 1 into this x box, and we'll get negative 1 to the n plus 1 over n, and I have x minus 1 to the n. So there would be a Taylor series for just the natural log of x centered at positive 1. Okay. We have to worry about intervals of convergence and things a little bit, but we can always compute those with the root functions. So let's go back up here to our list of common Taylor series, and I think I can undo this scratching out stuff. Let's get rid of the and do a +1 and start at 1, and that's what we had come up with for our Taylor series down there. So this is for x in R. The radius of convergence for the exponential function is everything. This is for x in R as well. The sine and the cosine both have radiuses of convergence which are infinite. But now this, we should probably have a problem because we've got that asymptote at 0. And if I check this with the lim sup of the nth roots of the coefficients, this is only good for x in absolute value less than 1. Right, this is centered at 0. If I went over to 0, that'd be going a 1 to the left. I can't go 1 to the left. I have to go less than 1 to the left. My radius of convergence is going to reach that first asymptote, and that's usually the case. The radius of convergence fails once you hit an asymptote. If I would center this at 2, my radius of convergence would probably be 2 because it would work until I hit that asymptote. There's no asymptotes on the right to stop me, so it's the asymptote on the left. If I went out to 50 and centered the natural log of 50 plus x, my radius of convergence would be 50 because to the left is where I'm going to hit that asymptote. That's kind of a good rule of thumb, but you have to worry about asymptotes in the complex plane, not just on the real line. So it's kind of how close are you to the first complex asymptote is going to be your radius of convergence. Let's do a couple other things with Taylor series now. So let's find the Taylor series for 1 over 1 minus x. This you might recognize. This is actually the sum of the geometric series x to the n, and so that's going to be our Taylor series from n equals 0 to infinity for this function. Let's see why that works. Say f of x equals 1 over 1 minus x. We'll center this at 0. F at 0 is equal to 1 then. I'm going to rewrite this as 1 minus x to the negative first. Okay, so f prime at x is going to be negative 1 times 1 minus x to the negative second times, I've got to use the chain rule, times a negative 1 because the derivative of 1 minus x is negative 1. At 0, we'll end up with 1 as well. F double prime at x. Well, I'd bring that negative 2 down, and I 1 minus x to the negative second, but I have to multiply by a negative 1. So I get a negative sign from the exponent every time I take a derivative, and I get another negative sign from the chain rule every time I take a derivative. I just get to multiply by that exponent in absolute value each time. This is going to be 2. The third derivative at x is going to be 3 times 2 times 1 minus x to the negative third. This should be a 3 up here, shouldn't it? Okay, and so the third derivative at 0 is 6, and so on. So C sub n, the coefficient of x to the n is going to be, well, the nth derivative at x is n factorial 1 minus x to the negative n plus negative n. So at 0 that would be n factorial. So that's going to be n factorial over n factorial. And my summation would be n factorial over n factorial x to the n from n equals 0 to infinity. That's going to be your 1 over 1 minus x, which just works out to be 1 over 1 minus x equals the sum from n equals 0 to infinity x to the n. Okay, so those are some common power series, Taylor series that we will use to manipulate and work with some Taylor series in the next video to calculate some integrals or find Taylor series of other rational functions, other things that we might be interested in.